Really, really pleased and honored to have been asked to speak today. And Roman asked me to give an introduction to quantum computing, which I will do and focus a little bit on superconducting qubits. And I won't be giving a lot of research results from my group in particular, but just giving more of an overview of the field. And I'm hoping to get back to Rochester on another occasion, maybe to give a more in-depth technical talk on my own results.
Welcome to today's deep dive. You've been digging into quantum computing, right? And you've got your sights set on a big name, William D. Oliver.
Smart move.
Yeah, this guy's a rock star. You've got some great info about him from his MIT and Lincoln Lab bios.
Definitely. Let's dive in.
Okay, first things first. This isn't just some MIT professor, right? This is William D. Oliver, the Henry Ellis Warren professor.
You don't get a title like that by accident.
No, you don't. And check this out. Joint appointment in electrical engineering and computer science and physics.
Wow.
That's some serious brain power right there.
What's fascinating here is how all those fields, electrical engineering, computer science, physics, they all converge in quantum computing. It's like he's positioned right where the magic happens.
Right, the perfect storm of expertise. And his research reflects that. Superconducting qubits, cryogenic packaging. This isn't just theoretical physics. This is hands-on, making it happen science.
Absolutely.
Now, for those of us who aren't quantum physicists, can you explain what makes these qubits so special and why they need to be super cooled?
Imagine a computer that uses the strangeness of quantum mechanics to solve problems that would take classical computers, billions of years. That's the promise of quantum computing. Superconducting qubits, they're the building blocks of this type of computer. They use the flow of electrical current without any resistance, which happens at ultra-low temperatures, to represent quantum information.
Okay, that makes sense. So it's like they need to be kept in this extremely cold environment to function, which is where the cryogenic packaging comes in.
Exactly. Imagine needing to keep something a fraction of a degree above absolute zero.
Wow.
Colder than the vacuum of space. That's what cryogenic packaging does. And Dr. Oliver's innovations, they're making it more reliable, more scalable, paving the way for, more powerful quantum computers.
It's like he's got one foot in the future and one foot firmly planted in the present, building the bridge between the two.
Okay, so are you ready to dive into something kind of wild today?
Always. What do we got?
Well, we're talking superconducting qubits.
Oh, cool.
Yeah, those tiny little things that might just power the future of everything.
It's true. They're pretty mind-blowing when you think about it.
It's like we're on the verge of something huge.
Yeah.
But sometimes I feel like I need a whole glossary of terms just to follow along.
Uh-huh. I know what you mean. Quantum physics has that effect on people.
It's true. But luckily, that's what we're here for, right? To break it all down.
Exactly. And trust me, the work this MIT expert is doing, it's making it all a little less science fiction and a lot more, reality.
Okay, see, now that's what I like to hear. Real-world breakthroughs. Because let's be honest, who hasn't dreamed of having a computer that can solve problems in minutes that would take our laptops, a billion years?
It almost sounds too good to be true, right? But that's the promise of quantum computing.
Okay, I am SO ready to have my mind blown. So how do we even begin to understand this?
Well, it all starts with rethinking how we view computers entirely. We're so used to ones and zeros, those bits, flipping on and off.
The digital heartbeat of our world.
Right, but quantum bits, or qubits, totally different rules apply there.
Oh, I bet. Quantum mechanics always full of surprises. Lay it on me. How do these qubits work?
So imagine a coin spinning in the air. Until it lands, is it heads or tails?
Well, both. And neither, I guess.
Exactly.
Yeah.
It's in this weird in-between state, that superposition, a fundamental concept in quantum mechanics, and it's what makes qubits so special. They can be in multiple states at the same time.
Whoa, okay. So instead of just a 1 or a 0, it's like this swirling mix of possibilities.
You got it. And that's what gives quantum computers the potential to be exponentially faster than classical computers for certain types of problems.
Okay, I think I'm starting to get it.
Yeah.
But how do you even build a computer out of these spinning coins?
Well, one of the most promising approaches uses something called superconducting qubits. And this is where that MIT research you were talking about comes into play. Oh, yeah. The experts' work. Tell me more.
So they're tackling the big challenge, how to build superconducting qubits that are powerful, but also super reliable.
Yeah, because I imagine it can't be as easy as just wiring a bunch of them together, right?
Not even close. It's way more complex than that.
Okay, so walk me through it.
So picture this. Each superconducting qubit is basically a tiny artificial atom
hold on. We're building atoms now. This just keeps getting cooler.
Right. And these atoms, they're not made of protons, neutrons, the usual suspects. We're talking superconducting circuits.
Superconductors. Okay, so those are materials that conduct electricity with zero resistance, right? Like superhighways for electrons.
You got it.
Yeah.
But how do we go from superconductors to atoms, right? Well, these circuits, they have this special ingredient called a Josephson junction.
Josephson junction. That sounds like it's straight out of Star Trek. Haha. It kind of does. But seriously, it's this tiny device, often made of two superconductors separated by a super thin insulator. And here's the mind-bending part. It lets current flow even without any voltage applied. It's like quantum tunneling.
Quantum tunneling, is that like walking through walls but on a subatomic level?
Basically, it's a quantum effect that allows electrons to bypass that insulating barrier. And this is what gives the Josephson junction its magic, allowing us to build those artificial atoms.
Okay, so we've got superconductors, we got these Josephson junctions doing their quantum tunneling thing, and somehow we end up with artificial atoms that can be in multiple states at once.
Exactly. And that's just the beginning. The MIT research you mentioned, they're finding that the way we design and control these superconducting circuits, it directly affects how well the qubit actually performs.
So it's not just about building these qubits, but also figuring out how to, like, choreograph them, make them dance to our tune.
That's a great way to put it. It's about precision and control on a whole other level. It really is. It's like, okay, we've built these incredible artificial atoms. They can be in all these states at once. But how do we actually control them? How do we get them to, do something useful?
Right. It's not like we could just, like, poke them with a really tiny stick and be like, do a quantum calculation.
I wish it were that easy. But no, it takes some serious ingenuity.
Okay, so what's the secret? How do we talk to these quantum atoms?
Well, one of the key tools we use is something called a microwave pulse.
Wait, like from a microwave oven, do they have to be preheated first?
Not quite. These are super precise pulses of electromagnetic radiation. It's all about fine-tuning the frequency and duration to nudge those qubits into specific quantum states.
So it's like we're speaking their language, sending them signals to tell them what to do.
Exactly. We're essentially manipulating the energy levels of these artificial atoms. Remember the Josephson junction?
Oh, right. The quantum tunneling thing, Imaji.
That's the one. It creates this unique energy landscape for the qubit. And by applying these microwave pulses, we can make the qubit jump between different energy levels.
Okay, so we're like quantum puppeteers, using these microwave pulses to make the qubits dance.
I like that analogy. It's all about precision and control. But of course, there's a catch.
Uh-oh. I was wondering when you were going to say that. What's the catch?
Well, superconducting qubits, they're incredibly sensitive to their environment. Imagine these tiny, delicate snowflakes.
Okay, I'm picturing it.
The slightest disturbance, a little noise, a vibration, it can knock them out of their quantum state, and that causes errors in our calculations.
So it's like trying to do high-precision surgery on a snowflake in the middle of an earthquake.
That's a pretty good analogy. It's a huge challenge. And this is where that MIT research really comes in. They've developed this really elegant solution called passive error suppression.
Passive error suppression. Okay, I'm intrigued. Tell me more.
So picture a lacrosse player running down the field with the ball. They don't just hold the stick still, right?
No way the ball would fall out instantly, especially with all that jostling and bumping.
Exactly. A skilled player, they cradle the ball, moving the stick back and forth to stabilize it against all those external forces. That's kind of what passive error suppression does for our qubits.
So we're basically giving those qubits a little nudge here, a little jiggle there to keep them on track.
You got it. By carefully engineering their environment and making these subtle adjustments, we can minimize the impact of noise and decoherence.
Decoherence, is that bad? It sounds bad.
Yeah, it's basically the quantum equivalent of a qubit having a meltdown. It's what happens when those environmental factors mess with the qubit's state and it loses its quantumness.
Oh, no. And we need that quantumness for all the super fast calculations.
Exactly. So this passive error suppression, it's like we're building a fortress around those delicate snowflakes, shielding them from the elements.
It's like giving them their own little quantum safe space.
That's a great way to put it. It's a game changer for building more reliable quantum computers. But it doesn't stop there. We've also got quantum error correction. It's like spreading the quantum information across multiple qubits, making the whole system more resilient to errors.
Okay, so it's like having backups upon backups.
Exactly. It's all about building redundancy into the system. And the exciting part, scientists are making incredible strides in understanding and overcoming these challenges.
That's what I like to hear. So all this talk about more reliable qubits, bigger systems, It makes me wonder, how do we actually scale this up? I mean, we can't exactly build a quantum computer the size of a house.
Haha, not yet anyway.
Mm.
But it's a question everyone's asking. And the future, well, it might not be about building out, but building up.
Building up, what do you mean?
Think of it this way. Remember how we talked about superconducting circuits being like miniature cities?
Yeah, with electrons zipping around like tiny cars.
Exactly. Now imagine building those cities vertically, skyscrapers, instead of sprawling suburbs. That's the idea behind 3D integration.
Quantum skyscrapers. I'm listening.
It's about building more compact and powerful quantum computers. Instead of just one layer of circuits on a chip, we're talking about stacking them, creating these intricate 3D structures.
So like a high-tech layer cake, but for qubits.
Exactly. It's all about using these tiny vertical pathways called through-silicon vias, or TSVs, to connect everything together.
TSVs. Wait, weren't we just talking about those?
We were. They're crucial for protecting qubits from noise. Remember our quantum fortress? Well, TSVs are part of the defenses, making sure signals can travel between layers without causing any interference.
It's like each layer of our quantum skyscraper has its own dedicated elevator system, keeping everything running smoothly.
Exactly. And because of that, we can pack in way more qubits without making the system physically bigger. Plus, the shorter connections mean less energy loss, which is a win-win.
Okay, so 3D integration, it sounds like a pretty big deal. But how on earth do they actually build something so incredibly complex? We're talking about microscopic layers, these tiny TSVs. It boggles the mind.
It really does. It's like the cutting edge of nanofabrication. They're borrowing techniques from the semiconductor industry, pushing them to the absolute limit.
So we're talking about building things atom by atom.
Pretty much. Growing thin films of superconducting materials, etching patterns with beams of ions. It's wild. And all of this has to happen while maintaining those super low temperatures that superconductors need.
Right, because these snowflakes are not going to build themselves. It's like performing surgery on a soap bubble while blindfolded and underwater.
That's one way to put it. It highlights the incredible complexity of this technology. But, it's this challenge that makes it so exciting. We're not just building machines, we're pushing the boundaries of what's possible.
So where does all this lead? What's the end game here?
The dream is to build a large-scale, fault-tolerant quantum computer. A machine that can solve real-world problems that are impossible for our current computers to even comprehend, let alone solve.
Problems that would take billions of years with today's technology.
Exactly. We're talking about things like designing revolutionary new materials, developing life-saving drugs, cracking the codes that protect our online data.
Maybe even unlocking the mysteries of the universe.
Who knows? The possibilities are endless. And the really incredible thing, we're just getting started.
It's like we've been handed the keys to a spaceship, and we're still figuring out how to take off. It's kind of like we've stumbled upon this whole new world, but we're still deciphering the language, the customs, everything.
Exactly. We're still in the early stages, but the progress we've made, it's remarkable, really. And the research you shared about this MIT expert, it just shows you how fast this field is moving.
Seriously, it's mind-blowing.
Yeah.
But for those of us who might be feeling a little like, whoa, I need a quantum physics crash course, what are the big takeaways? What do we absolutely need to remember about all of this?
Great question. I think the biggest thing to remember is this. Superconducting qubits. They're not just some sci-fi fantasy. This technology, it's got the potential to change everything.
It's like we're standing on the edge of a whole new era, like the digital revolution, but on a quantum scale.
Exactly. And while the technical stuff is fascinating, what really gets me excited, it's the creativity, the ingenuity. People are coming up with such wild solutions,
Right. Like those quantum skyscrapers.
Yeah.
Who thinks of this stuff?
I know, right? It's amazing. And it really shows the power of collaboration in this field. You've got scientists, engineers, all working together, pushing the boundaries of what's possible.
And to think it all started with this idea that, well, reality itself is a little bit bonkers. Things can be in multiple states at once. We're harnessing the weirdness of the universe.
And that's what makes it so cool. We're not just building machines, we're exploring the fundamental nature of, well, everything.
It's like that saying, any sufficiently advanced technology is basically magic.
I love that quote. And it's so true for quantum computing. Things that seem impossible today, teleporting information, simulating molecules atom by atom, that could be our reality tomorrow.
Okay, now that's a future I can get behind. But of course, it's not all smooth sailing, right? We've talked about errors, decoherence, scalability. What's the road ahead look like for superconducting qubits?
Well, that's the million-dollar question. But if I had to guess, I'd say keep an eye on how we control these qubits. Remember those microwave pulses?
Oh, yeah. Sending those signals, getting those qubits to dance.
That's it. But now, researchers are figuring out even more sophisticated control methods using light magnetic fields. We're talking about incredible precision.
So even fancier footwork for our quantum dancers.
Exactly. And error correction. Huge advancements there, too. New codes, new techniques.
Yeah.
We're getting closer and closer to those super reliable quantum computers.
It's like we're reinforcing those quantum fortresses, making them even stronger.
That's the idea. But honestly, maybe the most important thing, there's this global push to build bigger, more powerful quantum computers. Hundreds, thousands of qubits.
We're talking mega skyscrapers now. Quantum cities.
Exactly. And with that kind of power, we could tackle some of the biggest challenges humanity faces. New energy sources, climate change, personalized medicine. The possibilities are really endless.
It's exciting and honestly kind of daunting at the same time.
It is, but that's what makes this such a compelling field, you know? We're not just bystanders. We're shaping the future of technology, and in a way, the future of humanity itself.
Now, that is an incredible thought. So for everyone listening, get ready. The quantum revolution is here, and it's going to be one heck of a ride. Thanks for diving into the world of superconducting qubits with us.
It's been a pleasure.